Welcome to qiphyedu. Today we'll be looking at Computer Science October-November 2022 paper 11. Alright, so let's get started. Here's the first page and the first question. Convert the unsigned binary integer into denary. What does unsigned mean? Unsigned means that the number that you see here is not going to be differentiated into positive or negative number. It will just be a positive number. So now we're going to convert it into denary. So now let's look at the far right side of this number. So from the right hand side, since this is a binary number, we start with base 2. So this one here on the right hand side is power of 0. That would be the rightmost number. And then on the left, start to increment it by power. So the second digit to the right would be to power 1, then to power 2, all the way up to power 7. So here we can see that there's we need to calculate number to power 0, to power 1, to power 2. Then the 0 we can ignore. This is to power 3, to power 4, and this is to power 5. So to power 5 is 32, to power 2 is 4, to power 1 is 1, and to power 0 is to power 1 is 2, and to power 0 is 1. So this one we'll get 39. So the answer is 39. Okay. The second one here is convert the binary coded decimal into denary. So binary coded decimal, essentially this means that out of the 8 digits that you see here, the left 4 digits are for 1 digit in the denary form, and then on the right hand side, the right 4 digits is also for another digit in denary form, for example. So in this case, we're going to split into half. So here we have the left 4 digits and right 4 digits. So this one is on the right hand side is 0, 1, 1, 1, which means that it's 7. You can calculate it by slowly incrementing the number 1 by 1, and you can get 7. And then for 0, 0, 1, 0, this would be 2. So this is 27. For this number, you can also just add up the numbers by converting them to denary form, which is like 2 power 0, same thing that I did for the previous question, and then 2 power 1, then 2 power 2, and you still get 7. Same goes for this one. This is 2 power 1, so you get 2. Convert the 8-bit 2's complement binary integer into denary. So this number, the leftmost digit determines whether your number is a negative number or positive number. Since this number here on the left is basically 1, this means that this is a negative number, essentially meaning that we need to convert the number first into a positive number, and then we add a negative sign in front. So here what we're going to do is I'm going to convert it into a positive number. So this one is 0, 0, 0, 1, 1, 0, 0, 1. So we're going to add that up together, and we'll get something like this is 2 power 0, this one nothing, this one nothing. So this is 2 power 1 to power 2, and this is 2 power 3, and then 2 power 4. So we'll get 25, and because this is a negative number, because of the one on the leftmost bit, that means that we need to convert it to negative. So this is negative 25. Perform the following binary subtraction and show your working. Okay, so here let's see. 1 minus 1 is 0. 1 minus 0 is 1. And here, because it is 0, so we will temporarily not calculate this one. We will look at the leftmost number. So 1 minus 0, you get 0. 1 minus 0, you get 1. However, because you can see that on your second digit here, there's nothing, it's basically 0 subtract by 1, which is impossible. So we need to move the 1 on the left over to the right hand side. Therefore, even though 1 minus 0 equals to 1, since we're moving the 1 to the right hand side, it essentially becomes a 0 as well. So this one, our 1 moves to, we move to the right hand side, we get 10. 10 minus 1, we get 1, but because you can see that we have all these numbers here, minus is all 0, and then we have this leftover digit that cannot be subtracted. That means we need to move the numbers from the left to right as well for it to be subtracted. So 10 minus 1, we get 1, but because we want to move the 10 to the right hand side, so this one also becomes 0, and then this one we get 10 as well. Move over, so 11 minus 1, we get 10, and then since we are moving another 1 to the right, so we get 1. So we are moving 10 to the right, so 11 minus 1, we get 10, then 10 minus 1, we get 1, so we move the 10 to the right hand side. 10 minus 0, we get 10, but then because we are moving the 10 to the right hand side, so we get 1. And then we move the 10 to the right hand side, and 10 minus 1, we get 1. So this is the answer for this binary subtraction. Okay, now we need to give one similarity and two differences between the ASCII and Unicode character sets. Okay, so these character sets represents character, right? In depending on what form it could be in, it's basically mostly in binary form. And so what's the similarity between these two is that both can represent characters, different characters using a Unicode. Right? So what are the differences? ASCII, for starters, is either 7 or 8 bits. So in ASCII, we have either extended ASCII or normal ASCII. Normal ASCII is only 100 and it's basically 128 characters, whereas extended ASCII would be 256 characters. So essentially conveying that it will be either 7 or 8 bits. But for Unicode, you can go up to 32 bits. The second difference would be Unicode can be used to represent different languages, whereas ASCII is only for basically English. Like such. So yep, that's the difference. The similarity is that both can represent different characters using Unicode. Difference is that ASCII is either 7 or 8 bits, but Unicode can go up to 32 bits. And second difference is Unicode can be used to represent multiple languages, whereas ASCII can only be used for one language. And because of the existence of Unicode, we have like characters that can be represented in CJK characters, Chinese, Japanese, and Korean, and also in other languages that are not using alphabets. So this is the difference. Okay, so now we move on to D. Sound samples are recorded and saved in a file. So what is meant by sampling rate? So normally when we think of rate, we think of something like something per second. So here, sampling rate is number of samples taken per second. Explain the effect of increasing the sample resolution on the sound file. This is a 2-mark question, so we need 2 points. So when you increase the sampling resolution, this is the resolution, mind you, sampling resolution, this will increase the number of bits per sample, which increases file size. If you're on the safer side, you can also add one more point. Because when you have more number of samples, this makes the sound file more accurate. So it'll be much, in terms of sound quality, it'll be much better. So this makes the sound file more accurate. Right, so I'll move on to the next question. This is question 2. Alright, so draw one line from each security feature to its most appropriate description. Firewall is basically used to block incoming and outgoing internet packets. So data packets, sorry. So this one is definitely, if you look at the right, that will be on the bottom. So we will draw one line to the bottom. Right. Farming is basically when you click on you click on a link, but it redirects you to multiple links, but it redirects you to a fake website. Yeah, so when you click on the link, it redirects you to a fake website. This is called farming, instead of going to the original one. In your antivirus software, it's used to scan for malicious files, see if they have viruses or not on your computer. So this one will be scan files on the hard drive for malicious software. Encryption is when you convert your data into a different form than its original. So like for example, in encryption, we know that there is like ciphertext and all those that you convert by using hash keys and all those to convert the data into different types. Yep, so this one will be to convert the data into alternative form. Right, so that's the answer for this one. Okay, question 3, draw a logic circuit for the logic expression. So first of all, we look at the logic expression. It says not A and not B, or not B and not C. So when you look at A and B, it uses the AND logic expression. So we're going to put I'm going to put an AND symbol. Sorry. I'm going to put an AND symbol. So I'm going to draw one line. Yeah, something like that. Actually, not like that. This one is probably because of the shape recognition on the iPad. So I'm just going to draw to look like it, something like that. And then we're going to because it's not A and not B, so assuming this, you need to assume that everything here is 1. Okay, so in this case, we are going to convert everything to 0. So I'm going to convert it to 0. I'm just assuming that everything is 1, but let's say it's not, that means we need to convert it to 0, for example. So here we're going to convert it into not. Oops. So we're going to put a not expression here. Like that. I'm going to put this thing here, so it converts into a not expression. And then we put one line. Then this one we copy and paste. For the sake of convenience, of course. So, yep, like that. And then we'll draw one line as well. And then we link them up together to this expression. And then we're done with not A and not B. Now we need to look at not B and not C. So now we need to link not B and not C together. So now we need to use the same symbol as well. So then here at B, we need to put one big circle, or I would say a large dot, and then draw one straight line, linking these two together. And because this one is also N, so we're going to draw an N symbol, like such. Right. I'm gonna move this so it looks better. Okay, and then link them up together because there's an O in the middle. We're actually already done with this part and also this part. So now we need to link them up together using the OR expression. So this one, oops, just draw one line down. It goes here, it's up. We link that together. And then we're gonna draw an OR symbol. This also requires a bit of work. that, and then this is not A and not B, or not B and not C. So here we also need to draw a NOT expression after we connect everything together. So it will be something like this. Then we link it up with X, and then that's it. Okay, this looks a bit different. I'm gonna move it down a little. Right, there you go. And then complete the truth table. So now we assume that A, B, and C are all 0. So since this is not A and not B, 0, 0 become 1. So this one would be not A and not B, that would be 1 and 1. Or so it's not 1 or 1. So since this is not 1 or 1, this is immediately a 0. Okay. Because if you, let's say, okay, so just convert this into working space, this will be something like this. So not A is 1, not B is 1, or not B is 1 and not C is 1. So 1 and 1 is 1. 1 and 1 is also 1. So 1 or 1 is 1. But not 1 will be 0. Right? Same goes for the second one. We also draw like this. 1 and 1. Or 1 and 0. Because now C is 1, so not 1 will be 0. So 1 and 1 will be 1, and 1 and 0 will be 0. So 1 or 0 will still get 1, so not 1 will be 0. Okay, then the next one, B is 1, so 1 and 0, or 0 and 1. So both of these will give you 1, because 1 and 0 is 0, or 0 and 1, 0. So 0 or 0, you get 0, not 0 will be 1. Okay, the fourth one will be not 1 and 0, or 0 and 0. This one you'll get 1 as well, because 1 is 0, 0, and 0 and 0 is 0, so not 0 will be 1. Here is not 0 and 1, or 1 and 1. 0 and 1 you get 0, 1 and 1 you get 1, so 0, 1 you get 1, so not 1 will be 0. And then next one would be not 0 and 1, or 1 and 0. So this one you get 1, and then not 0 and 0, or 0 and 1. So not 0 and 0, you get 0, and 0 and 1 still be 0, so not 0 will be 1. And then this one, last one, not 0 and 0, or 0 and 0. So this one you get 1 as well. Alright, so there we go. A photographer creates a relational database to store data about photographs taken at birthday parties. The database photograph stores details of the customer, the party, the photographs taken, and the cameras used. The photographer has several cameras that are used, so that means that there are many cameras, and then each camera has a specific whatever this is, because honestly, if you look at the entity relation diagram, is not very, doesn't really cover that much of lenses and all those, but it's more like photos, cameras and all those. So each camera has a specific lens type and lighting type. Data about each photograph is stored in the database, including the party which it was taken, and then the database has 4 tables. Right. So now, for one birthday party, normally there will only be one customer registering for it, but there can be many parties, right? So a customer could be at many parties, and they would probably hire the photographer to take pictures at multiple parties. So this would be one to many, one customer, many parties. And then because in a party there could be many pictures taken, so there will be one party and a bunch of photo data. So it would be something like this. And then a camera can be used to take pictures of multiple cameras. But if you look at the database here, you can see that camera ID is actually a foreign key under photo data, and then camera ID is actually the primary key of camera data. So because camera ID is a primary key under camera data and camera ID is under foreign key of photo data, that means that for one camera data there can be many photo data. So that will also be a one-to-many relationship as well. Same goes for the others as well. As you see under customer ID is primary key for customer and also foreign ID for customer ID, which means that there could be many parties that the customer has, right? So that's why for customer to party there will also be a one-to-many relationship. Same goes for the camera data and photo data. Like such. Alright. The database is normalized and is in third normal form. Describe the characteristics of a database that is in third normal form. So for third normal form, if based on text, that would be it's in second normal form and there's no transitive dependencies, right? So you can say there's no partial dependencies. No transitive dependency. And there are no repeating groups of attributes, which is exactly what we see in the relational database before this. Alright. The table shows some sample data for the table photo data. So say what is meant by a tuple and give an example of a tuple. So this is considered a row. This is considered a column. So a tuple would be a single row in the table. And then example would be you can write something like this. Example of a photo data table, it could be something like this. Like something like that. And then complete the structured query language. Script to display the total number of photographs that have been taken with the camera, starting with can. So calculate the total number. So this will be count. And then total number of photographs, that will be photo ID. So all the pictures will be from photo data. Camera ID like. So this would be can, like such. Okay. Write an SQL to include two new fields in camera data to store the number of photographs currently on the camera and the date the camera was last used. So we need to add two new fields in camera data. So if you look back at camera data, we have camera ID, lens type, and lighting type. So we need to add two more. So we're going to alter the table. So alter table, camera data, and we're going to add, because we need to store the number of photographs currently on the camera, so this will be number stored. So this will be integer. And then the date the camera was last used, so this will be last used. And this is date. Then we put a semicolon. That's it. And then we move on to the next question. State what is meant by the stored program concept. So this is in the von Neumann architecture. So this would be instructions in data. Are stored in the same memory space. Okay. So state the role of the following registers. The program counter will be used to store the address of the next instruction. Either next instruction to be fetched or to be executed. In this case, I'll put to be fetch. The next register to store a value that is added to an address. To give another address. And then your status register is to store flags which are set by events. Okay, so these are the three purposes of these special purpose registers. So PC will be to store the address of the next instruction to be fetched, and then IX will be to store a value that's added to an address to give another address. The status register is to store flags which are set by events. Tick one box in each row to identify the system bus used by each CPU component. So system clock is definitely under control bus because that's how you control the entire CPU. And then your memory address register. So when you see address, immediately think of the address bus. Describe the purpose of the control unit in a CPU. So control unit is used to synchronize actions of other components. And also to receive control signals along the control bus. Right? Describe the purpose of an interrupt. To send a signal from a device or process that would seek the attention of the CPU or seek the attention of the processor. And then identify two causes of a software interrupt. So normally when there's a software interrupt, it's mostly because there's an error in your program. So this would be, you can say, runtime error. Second, you could say attempt to access an invalid memory location. Right. Following table shows part of the instruction set for a processor. The processor has one GPR or general purpose register, the accumulator, and an index register. Here are all the instructions, the opcode and the operand, right? So now we move on to the next question, which is the current contents of main memory and selected values from the ASCII character set are given, and then trace the program. So now we're going to trace the program. So first of all, the first row has already been drawn for us. So now we're just going to move on to the first instruction, which is address 77. And then it says LDR #0. So we need to load the instruction LDR. So look at LDR, it's immediate addressing, and we load the number n to ix. So this is #0. So that means we just take the number from here and we put into the index register, which is 0. We move on to address 78. So this is index addressing 110. So index addressing of 110, you form the address from address plus the contents of the index register. So LDX 110, you'll get 66, and then this will be loaded onto the accumulator. And then we move on to the next instruction, which is CMP35, #35. So we compare it with the number in the accumulator, if I'm not mistaken. Yes, compare the contents of the accumulator with number n. Number n is 35 and the accumulator is 66, so nothing happened. We just move on to 80. So AJPE is that you'll jump to address 92 if, let's say, the comparison was true. Since the comparison is false, we just jump to 81. Okay, 81 is you add 100 to, we add the accumulator's number value into memory address 100 because there's no hashtag in front, so we are adding it into the memory address. So this one will be at 100, so in that area we'll put 66. And then 82, so add 100 would be, you add, would be when, okay, let's look at this. So add the content of the given address to the accumulator. So here add 100 means it's 0, so nothing happens because we are adding the value of the memory address to the accumulator, so incrementing it with the value in the memory address, but there's nothing in 100, so it's 0, so we just jump to 82, and then we store the value in the accumulator into 101, so this would be 101, we put 66, and then 83 is LDM1. So LDM1 here means that immediate addressing, load the number n into accumulator, so LDM1, so we're just gonna load the number 1 into the accumulator like such. And then 84 is basically add 100 as well, but since it's still 0, we just ignore it, and then we store the number in 100, so this will give us a 1. And then 86 would be increment the ix. So when you increment the ix, you'll get 1 because the index register was originally at 0. And then 87 would be LDX110, 87 would be LDX110, so we're going to load direct LDX110, so we'll get 60. You will get, since this is the index register, so we need to add it as well. So 110 we plus 1, you get 111, so 111 here is 65, so we just put 65 into the accumulator. And then 88 would be to compare 35, since it's still false, we can just ignore JP and 81. And then we just go to 89, so J89 is basically 89 is basically JPN 81. So JPN is when it's false, so since it's false, we're going to jump to 81. So 81 here will be to add 100. So 100 here is still add 100, still be it's actually 1, so we add into the accumulator, we get 66. 82 is stored in 101, so because the number of 81 and memory address 101 is basically the same, so technically you can just ignore that and just move on to 83. 83 here, LDM1, so we're still going to load 1 again, and then 84 will be increment, will be to add 100, so add 100 you still get 1 plus 1, so you get 2. 85 would be to store the number into memory address 100, so you get 2. And then 86 would be increment the index register, so we'll increment it, we get 2. And then 87 we get LDX110, so LDX110 index, so that will be 110 plus 2 because the IX is 2, so we get 35. And then we're going to compare it with 35, which is true, and then because it is true, we just ignore 89 and we move on to 90. 90 is direct, is LDD 100. LDD 100 we'll get, so LDD 100, let's see, LDD is direct addressing, load the contents of the location, the given address. So LDD 100, LDD 100 is 2, so 2 is 50, so SQL 50, like, LDD 100 would be 2, so this would be 2. This is direct addressing, so we just take the number from 100 and we put it in here into the accumulator. 91 will be to add number 48, so this will get 50, and 92 will be to output the number, so number is basically 2, so we can output it on the right hand side, so this will give us 2, and then 93 is N. Yep, so there you go, there it is. Okay, state the purpose of this part of the assembly language program. Following instructions are repeated. So this one LDD 100 store 165. So LDD 100, it loads the content to ACC. So we load it to ACC. For example, LDD 100. Let's say 100 is 5. Store it at 165. And then LDD 101. Let's say it's 3. You need to store it at 100. And then LDD 165, you get 5. And then you store it at 101. So like that, it swaps around the numbers. So swaps the content. Memory address. Okay, so this is the next question. The following table shows another part of the instruction set for the processor. So here are all the instructions and also the opcode and operand. So now let's take a look at the current contents of the ACC. So B here, it says, this B here, it denotes a binary number. So this means that it is a binary number, so technically we can ignore this one. And then the current contents of the ACC are 10010011. Show the results after the execution of the following instruction XOR 0001111. So let's just write it on the right hand side. So this will be 10010011 and then 0001111 or XOR. So if it's XOR, we know for a fact that 0 XOR 0, we get 0. 1 XOR 0, we get 1, and 0 XOR 1, we get 1, and then 1 XOR 1, we get 0. Right? So here, 1 XOR 1, we get 0, 1 XOR 1, we get 0, 0 XOR 1, we get 1, 0 XOR 1, we get 1, 1 XOR 1, we get 0. Same goes for the left, 2, and then the last one on the leftmost bit would be 1 XOR 0, we get 1. So the answer would be 10001100. Technically we can write down here, so this will be 10001100. The current contents of the accumulator are 10010011 and show the results after the execution. So 10010011, 11110000. So N. So this will be N. So in this case, 0 and 0 we get 0. 1 and 1 and 0 we get 0. 0 and 1 is also 0, and 0 and 1. 0 and 1 is also 0, and 1 and 1 would be a 1. So 1 and 0, 0, 1 and 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, and 1. So this one would be 1, 0, 0, 1, 0, 0, 0, 0. So this would be 1, 0, 0, 1, 0, 0, 0, 0. Alright, so this should be the correct answer. Yep. 3. Current contents of the ACC are 10010011. Show the result of the execution of 11001100. So this will be OR. So for OR, 0 or 0, you get 0. 1 or 0, you get 1. 0 or 1, you get 1. 1 or 1, you still get 1. This is different from XOR. This would be the differentiating point. Alright? So 1 or 1, 1. 1 or 1, 1, 0, 1, 1, 1, so 1 and this is 0. and 1, 1. So this would be 1, 1, 0, 1, 1, 1, 1, 1. Okay, the last one would be current contents of the ACC are 10010011, and it says LSR2. Now, what is LSR2? LSR2 would be to shift the accumulator's numbers logically n places to the right. Here it says 2, so you need to shift it 2 places to the right, which means we eliminate this thing, and then we introduce zeros on the left. So this would be 001, 0, 0, 1, 0, 0, right? So let me write it down here. Like such. Take one or more boxes to indicate which one is the first pass assembler or the second pass assembler, right? So remote comments will be the first pass assembler. Read the assembly language program one line at a time. That would be first pass and also second pass. Generate opcode would be to be the second pass, and then your opcode is in the instruction set would be your first pass assembler, right? So that's for your assembler. And then 7, show 2 benefits of using DLL. So basically, DLL, the benefits would be to well, basically we don't need to maintain the DLL. Like such. And then 2 would be to executable file size is smaller because it does not contain all the library routines. Right, B, memory management is one of the tasks performed by an operating system. Describe the ways in which memory management organizes and allocates random access memory. So RAM is assigned into blocks. It reclaims unused blocks of RAM. And moves data from secondary storage when needed. Right? An operating system may include a utility program to compress text files. So normally for text files, right, we do not use loosey compression. This cannot be used. We use looseless. So looseless compression, that would be looseless compression, which is run length encoding. This replaces repeated sequence of characters. By a single copy, by a single character, and a counter of the number of characters. Okay, so now we move on to the next question. Explain the reasons why increasing the amount of cache memory can improve the performance of a CPU. So basically, cache would be one memory that is the closest to the processor. So in this case, we will say cache is fast access memory. And then it stores frequently used instructions. This is what it's used for. It stores instructions for the CPU. So it stores frequently used instructions So more cache memory means more instructions that can be instructions that can be transferred, and there's less swapping. Between RAM and cache. So that's why when you increase the amount of cache memory, it improves the performance of the CPU. Now state the name of the peripheral device port that provides a physical connection in the computer for each of these peripherals. Now 3D printer, normally, since we are now in the 21st century, normally we'll use a USB port. Back then you still have like a communications port, like probably a serial port or a parallel port, but those are in the 90s. So now today we all use, for mostly for 3D printers, we use USB ports. And then for the monitor, normally we'll be using HDMI, but there are still there's still quite a lot of monitors today that still use a VGA legacy, or we will consider a legacy monitor port, and also a display port. We rarely see monitors with USB ports. That's quite uncommon, but we normally will see HDMI ports and all those, and also display ports today for most high-end monitors. Most low-end monitors today will still use HDMI or VGA, sometimes DVI, which is not listed. If you go to the answer scheme, it's actually not listed, but DVI is also considered an option, right? So a local area network uses a bus topology. Describe how CSMA CD is used in a bus network. Carrier sends multiple access. So normally, this is how a bus network would be like. So let's say this is device 1, and this is device 2, and here there's a terminator, and then this is device 3, and there's another terminator. So one line, and the one line connects to this cable. So basically, we need to explain what CSMA is. So I'm just going to write in short form. Please don't do this in exam. So CSMA CD is a protocol used to detect and prevent collisions. So before transmitting, the device checks if it's busy, if the channel is busy. If it is, the device waits because there is more than one computer connected to the medium. If a collision is detected, by the device, transmission is aborted, or basically cancelled, but in a more computer-like term, we say aborted, and both devices wait a number of seconds or random time and try again. Right? Many modern televisions are examples of embedded system. Explain why these TVs are embedded systems. So essentially, a TV is basically used to connect to a satellite using maybe your satellite dish, and most TVs can only do one function, which is either that, or you connect to a monitor, connect to a computer, and then have the display sent over to the TV. So why is it an embedded system? Is because, first of all, the embedded system is built into the TV. And the firmware or the system is not easily upgradable. Right. Embedded systems use EEPROM. What's the benefit of using EEPROM? Is, first of all, it can be erased and reprogrammed several times. which allows firmware to be updated and it can be reprogrammed without having to remove it from the device. Okay, so that's it for this paper. I hope you can get a better insight as to how to answer questions like this in Computer Science Paper 1. And I'll see you again in the next video when we talk about more computer science past year papers. Till then.